For those of you that are still with us, hello and welcome to the first part of chapter number 5 in this lecture series on CCNA cybersecurity operations with me, Joachim Kjærestad from the University of Skövde. We left off having talked about different network techniques and network protocols and addressing that takes place for data to be sent over a network. And in this chapter number 5, we will talk more about network infrastructure, the actual devices that makes this communication happening. And this lecture is divided into 3 parts, where we will begin with the network communication devices, mainly networks and switches, and we will talk a little bit, or routers and switches. We will talk a little bit about wireless communication. And then we will talk about network security infrastructure in the next class, and we will end up with some representations of networks, topologies and architectures, how you build networks and how you represent networks essentially. So going on to device types, as we talked about before, you can broadly classify network devices into one of 2 groups, where we have end devices or hosts, and those are all devices that are at the network end and include smartphones, PCs, servers, printers, etc. Then we have the intermediary devices, and those are devices that are used to forward network traffic, so those that are in the middle of the network, if you will, such as routers and switches. So let's begin with talking a little bit about the router and the role of the router. So the routers operate at the network layer, layer 3 of the OSI model, and it have 2 primary functions. The first function is path determination, meaning that the routers are like post offices. Whenever you have, the role of the router is to receive packages that are destined for some network, and based on what the router knows about the rest of the world, decide where to send this package to reach the destination. The second one is packet forwarding, and packet forwarding is accomplished by a function that is called switching, or a switching function, and this is essentially the function of accepting a package on or a packet on one interface and then forwarding it out another interface. When it comes to path determination, the routers use IP addresses, so it's a layer 3 device that uses IP addresses to decide the best path forward for a packet. So how this happens in theory is, remember, we have the OSI model with those 7 different layers. And when a PC, in this case PC1, wants to send something to PC2, it takes whatever is on the application layer, maybe it's a web package, an HTTP package, or an email, and it goes through the OSI model, and there is a new layer of information added at each layer. So at layer 4 we have the port numbers, at layer 3 we have the IP addressing, at layer 2 we have the MAC addresses, and at layer 1 we convert the package into bits that can be sent over the medium. Then when the package arrives at the first router will unpack layer 1, 2, and 3 to get to the IP address, and it will examine the IP address and make a decision on where to send the package. Then it will repack the layer 3, it will repack layer 2 and add a new destination MAC address, it will repack layer 1, send it along its way, and so on and so forth until it reaches the destination where the whole packet will be decapsulated, and the actual application layer data will be revealed and used by the recipient host. So a big part of routers is to manage routes, and routes are essentially ways to remote networks. So a router contains something that is called a routing table, and a routing table is basically a listing of directions to remote networks. And a router should essentially know about all other networks in the world in a way. Usually you configure a router to know some of the closer networks, like all networks in your organization and maybe some other networks, and then you have something that is called the default route. And the default route is basically where you send everything you don't know about, and it's like a hierarchical structure of routers out there. So you send your packet to some more important router, and you hope that that router has a better view of the world than you have. So there are 2 types of routes in the routing table. We have the directly connected routes, and those are routes to all the networks that a router is directly connected to. Essentially, every router port is its own network, and the router, of course, knows about those directly connected networks. That's nothing weird. Then we have remote routes, and remote routes are essentially routes to anything that is not directly connected. There is also a number of ways in which a router can learn new routes, and we're not going to dwell on this too much, just for your information. So we have local route interfaces, and those are specific, special routes to the IP address of the local interface. Then we have directly connected interfaces, which is routes to the local networks. Those are automatically learned when an interface is configured. Then we have static routes, that is routes that we manually knapper into the router. And then we have dynamic routes, and those are routes that are learned using some dynamic routing protocol that routers can use to exchange routing information. Let's have a short look on how the router makes a forwarding decision. So just very briefly, when a package arrives on an internet or on an interface, when a router receives a package, it will look at the IP address, the destination IP address in that package, so to see where the package is going, and then it will look through its routing table and see if it knows a route to the destination network. So if there is a match, then the router will first look, is this a directly connected interface? Because if it's a directly connected interface, then it's something that should go out on a local network, right? If so, it will check its ARP cache or do an ARP request if necessary and forward the package to the appropriate host on the local subnet. If it's not destined for a directly connected network, it will see if it's a remote network. If it is, it will encapsulate the frame with and forward it out to the next hop. The routing table will specify the remote network and the next router to the next router in the chain, and the local router will send the packet there. If it's not for a remote network, then the router will see if there is a gateway of last resort or default gateway available. If it is, it will send the package to the default gateway. If it's not, then it will just drop the package because the router doesn't know where it's going. So that's the extremely brief introduction to routing. We handled this in about, this is like one full CCNA course worth of information, perhaps not really, but this is very condensed. So we're leaving the routers now and we're moving on to switches. And switches are used to connect devices into a local area network. And switches forward frames based on MAC addressing and maintains a MAC address table that stores information about what MAC address that is connected to what switch port. So just as PCs will have a mapping of MAC addresses to IP addresses, the switches don't have any IP address. Instead, the switch have a number of ports and will keep a MAC address table that tells the switch what MAC address to find on what port. So when a switch receives an Ethernet frame, it will examine the source MAC address, the sender MAC address, and add it to the MAC address table if it's not already present there. So it will try to learn MAC addresses in that way. And then it will examine the destination MAC address and send it out to the appropriate port. If it so happens that the switch doesn't know about the destination MAC address yet, it will just flood the packet out all ports except the ingress port. And the MAC address actually have a limit on, or the MAC address table is limited to a number of MAC addresses. The number varies depending on switch make and model, but there is always a limit on how large the MAC address table can be. And if the MAC address table gets full, then the switch will default to this flooding behavior, and that's actually important for an important security topic, because something that attackers commonly do to switches is that they flood the switch with frames, but they make sure that every frame have a new MAC address in it. And in this way, it can force the switch to fill up the MAC address table, and then the switch will flood any incoming packet, no matter what port it's coming in on. And this will heavily reduce network performance and also possibly allow an attacker to connect to the network and listen in on any traffic. So, switches, as I said, what they do is that they connect devices into one single local area network. So if you combine a number of switches and chain them together, they will still make out one large local area network, and that is desirable for many reasons. But on the other hand, you still want a way to be able to segment your network. So for instance, you may have a switched network within a campus or within an organization, but you still want some inter-organizational segmentation. And there is something called virtual local area networks, or VLANs, that allows you to do just this. So VLANs allow you to create several logical local area network on a single switch, or you can have VLANs that span over several switches. Like in the picture here, we have 2 different switches, and both switches are configured with VLAN 1 and VLAN 2, and effectively this configuration makes VLAN 1 one local area network and VLAN 2 another local area networks, and those VLANs cannot communicate with one another without having the packages traverse either a router or a layer 3 switcher with a routing function. So, moving on to something completely else that is very complicated to discuss in one picture is a spanning tree. But I just want you to show this picture because something that you do when you build a switch network is that you try to implement redundancy. So just remove this stop sign in your head for a little while and see that what's done here is that there are actually redundant ways in this network. So, for instance, a package traversing from one of the PCs down here to PC4 can go to switch 2 and then either take this direct way or take this way that is a little bit more complicated. What this creates is a scenario where it doesn't really matter if this link goes down, because packages can still take this way. The problem with this is that we have a circular configuration here, which makes it possible for loops to occur. It's very possible for a frame to enter here and then just loop around in the network, causing what is called a broadcast storm. And the problem with a broadcast storm at layer 2 is that there is no time to live field in the Ethernet frame, and that causes the frame to just loop around, and that happens until the switches die. So that's a very simplified explanation of the problem, but the solution is to implement something that is called spanning tree. And spanning tree is a protocol that dynamically removes all links. So it's built on a mathematical function that just calculates the shortest path between every switch and then disables the links that are not needed at the moment. So in this case, this link would be disabled, making sure that this is the only loop-free way. But if this link goes down, then this link will come up, so we also have redundancy at the same time. So let's end with saying a few words about wireless communication. I'm not really an expert in wireless communication, but I've tried to make sure to cover the topics that seem likely to appear on a certification test. So using VLANs, or wireless local area network, we can connect devices using radio frequencies instead of physical cabling. And basically, this provides us with more flexibility. It's easier to walk around. We can connect to bring your own devices. We can connect IoT devices with more ease, and we're not bound to a physical location for internet access, which is also very nice. However, this introduces more privacy issues since, the radio frequency reaches a larger area than a cable. So we have to consider the attack vector. If I want to listen in on the communication that is traversing a cable, I need physical access to the cable. But if I want to listen in on wireless communication, I need to be in, somewhat close proximity to an access point, and that is a much larger attack vector. I often don't even have to be within the same building as the access point. So trying to just compare wireless local area networks using the 802.11 standard with Ethernet local area networks. So on the physical layer, the media, we use radio frequency instead of fiber optic cable or copper cable. The media access part is not something that I want to discuss with you because that would take too much time. The availability is that anyone without a radio NIC or wireless NIC that is in range of the access point can, in theory, access the wireless local area network, whereas you need a cable connection for the cable network. And then if we talk a little bit about regulation, wireless local area network have additional regulation by country authorities that, for instance, tell you which radio frequencies you may use to send data and what frequency bands that are allowed. Whereas the Ethernet local area network is dictated by IEEE standards completely. So let's look a little bit at the operation of wireless local area networks. So a wireless device, to communicate, it must associate with an access point. So it must find a wireless access point, and it must associate with it before communication can occur. And to do that, management frames are used, and they are used in a three-step process. So first, the client has to discover a new access point, then it has to authenticate with the access point, and then it has to associate with the access point. And during the association, the client and server must agree on certain parameters. And the parameters are, for instance, the network mode, which is what standard to use, and SSID, the name of the network, the channel settings or the frequency bands to use for data communication, what security settings to use, what encryption to use, which should, by the way, be AES, and what password to use, because the client needs a password to authenticate to the access point. And I know for a fact that it's important to talk a little bit about the modes of operation, because this was a question on my certification exam. And a client must discover an access point it wants to connect to. And this process can be done in one or two ways. Passive, referring to the client being passive, and this is where the SSID is openly advertised by the access point. So passive is when the access point actively or openly advertises the SSID. Or active, where the client must know the SSID. So this is where you would type in the SSID of the access point. And there were originally two authentication mechanisms in the 802.11 standard, where the first one is open authentication, which essentially is no authentication at all. Anyone that wants to be authenticated gets authenticated. You just say, hey, I want to be authenticated, and the access point says, well, okay. And then we have pre-shared or shared key authentication, which is much better. It's based on a pre-shared secret, such as a certificate or a password. So that was actually it for the first lecture on network infrastructure. When you get back for part 2, we're going to go through some security infrastructure, and we're getting in on the security parts of this course. So as always, feel free to leave questions in the comments field, and until next time.